In this video, we're going to prove that the limit as theta goes to 0 of sine theta over theta is equal to 1. This fact is going to be very useful for us later when we're figuring out derivative rules for trig functions. So this is kind of a tricky proof. I don't expect you to reproduce it, but I would like you to try to follow it, and it is a good review of what you know about trig functions. So remember that the Squeeze Theorem says that if for all x in some open interval containing c, h of x is squeezed between f of x and g of x, and the limit as x goes to c of f of x is equal to the limit as x goes to c of g of x is also equal to L, then the limit as x goes to c of h of x is also equal to L. And there's an image kind of illustrating that idea. So to use the Squeeze Theorem to prove what we want to prove, that the limit as theta goes to 0 of sine theta over theta is equal to 1, we must show that there are functions f of theta and g of theta such that f of theta is less than or equal to sine theta over theta, which is less than or equal to g of theta, and the limit as theta goes to 0 of f of theta is equal to 1, and the limit as theta goes to 0 of g of theta is equal to 1. So we have to be a little creative in finding those functions, and to do that we are going to use the unit circle with radius 1 and a sector of that circle. So let's first think about a couple areas. So we know that in general the area of a circle is pi r squared. So the area of a circle with radius 1 is pi times r squared, but r is 1. So area of a circle with radius 1 is just pi. What about the area of a sector of a circle? So you might be less familiar with that formula, but the formula for that is 1/2 r squared theta. And so in our case, because the radius is equal to 1, the area of a sector with radius 1, if its angle is theta, will be 1/2 times 1 squared times theta. 1 squared is just 1 again, so that's just 1/2 theta. So that's the area of this sector, this like slice of the pie. And let's just color in that pie slice so that we know what we're talking about. The area of that sector in there is going to be 1/2 theta. Now we're going to think about two triangles. We're going to think of the triangle that begins here and drops down, and we'll label that triangle as as having points A and B. And we're also going to think of the triangle that starts here and goes up. So this triangle, we're going to call that CD, those 2 points. And each of those is a triangle, of course, with the origin 0, 0, we'll call that O. So let's think about each of those, the lengths of each of these line segments, the length of the line segment AB, the length of the line AB, of the line segment AB, so from A up to B, the length of the line segment OA, this one down here, and the length of the line segment CD. So let's think of each of those lengths, and maybe I'll actually pause and let you think about that for a moment before we talk about it. Think back to the unit circle and the definition of trig functions. How is sine defined? How is cosine defined in terms of angles of the triangle on the unit circle? Okay, so to answer this, let's think back to our trig functions. We know that sine of theta is equal to the opposite over the hypotenuse. So this is if we've got a triangle with angle theta, and the triangle that's made by that angle, sine of theta is the length of the opposite side, so opposite over here, divided by the length of the hypotenuse. Because this is a unit circle, the radius is 1, so the hypotenuse is 1. And so this is opposite over 1. And so in terms of theta, the length of AB is equal to sine of theta. Sine of theta is this opposite side length of the triangle AB, so of that smaller triangle. And so that's the length of the line segment AB. What about the line segment OA? Well, cosine of theta is the adjacent angle over the hypotenuse. And again, our hypotenuse is 1, so it's the adjacent over 1. And what is the adjacent angle? Well, that is our adjacent angle to the angle theta. And so that is OA over 1, or just OA. And so that, therefore, the length of OA is cosine of theta. To find the length of CD, we have to be a little creative. We're going to use the fact that these two triangles are similar triangles. So we've got two triangles here. Our original small triangle that contains the lengths OA and AB. And then we've also got our larger triangle. And we know, one of the lengths of this larger triangle, we know that the length of OC is equal to 1 because that's the radius of the circle. So what about the length of the line segment CD? Well, for that, again, we're going to use similar triangles. So we can use the fact that because they have the same angle, they're similar. And so the height over the width of the big triangle is going to be equal to the height over the width of the little triangle. So what do we know? We know the width of the little triangle is OC, or 1. The height of the big triangle, that's DC. We're trying to figure it out. So that was DC, or CD, over OC. And we know that's equal to the ratio of the height of the little triangle. Height of the little triangle, we figured out, was AB over height of, or width of the little triangle is OA, and we figured out above that that's sine of theta over cosine of theta. So then we know that DC is equal to sine theta over cosine of theta, H, because the bottom OA is just equal to 1. Great. So the length of CD is, we could write that as sine theta over cosine theta. If we wanted, we could also write that as tangent of theta. Okay, so why are we interested in those things? Well, our goal is going to be to squeeze some things, right? So what we're going to do is say, we've got the area of the small triangle, and that area is going to be less than or equal to the area of the wedge, the pie slice, which is less than or equal to the area of the large triangle. So we've got our wedge, that was that pink highlighted pizza pie piece. And then we've got our small triangle, so our small triangle in black, and our area of the large triangle, our large triangle in red. And so clearly that's going to be true for any angle theta. And so this will always work no matter what theta is. Now let's just figure out what each of those areas is equal to. So the area of the small triangle, it's 1/2 times the base times the height. The base is O times A, and the height is A times B. Less than or equal to the area of the wedge. We found that above and saw that the area of the wedge was 1/2 times theta, which is less than or equal to the area of the large triangle. So that's OC 1/2 times OC times DC. So both using the fact that the area of a triangle is 1/2 times the base times the height. So we found some of these values. So this tells us that 1/2 times OA was cosine of theta, times AB was sine of theta, less than or equal to 1/2 theta, less than or equal to 1/2 OC is 1, times DC. DC is sine theta over theta, sine theta over cosine theta, or tangent theta. I'm just going to leave it as sine theta over cosine theta. And now what can we do? We can do some dividing by 1/2. So there's a 1/2 in everything, so we could divide everything by 1/2, and that's fine. Let's just simplify to that step right now. So cosine theta sine theta less than or equal to theta less than or equal to 1 times sine theta over cosine theta. Now let's think back to what we're trying to do. We are trying to squeeze sine theta over theta between two functions. So I can now divide by sine theta on all sides, and I've got that cosine of theta is less than or equal to theta over sine theta, which is less than or equal to 1 over cosine of theta. One thing to note is that we divided by sine theta. Sine of 0 is equal to 0, but remember that we're interested in the limit as theta approaches 0, and therefore we're not interested in the exact value when theta is actually equal to 0. We're just looking at values of theta that are close to 0 but not equal to 0. And so dividing by sine theta is okay. We are not dividing by 0. So we're actually interested in sine theta over theta, so we can invert all sides of that inequality, and doing that will flip our signs. So flip our fractions and our signs. 1 over cosine of theta is greater than or equal to sine of theta over theta, which is less than or equal, which is greater than or equal to cosine of theta. Okay, so great. Now we've got sine theta over theta sandwiched between two functions. Let's now think about what happens to each of those as theta goes to 0. So we know that cosine looks like this, and we know that cosine of 0 is equal to 1. So the limit as theta goes to 0 of cosine of theta is equal to 1, and the limit as theta goes to 0 of 1 over cosine of theta, that's 1 over 1, and that's 1 as well. So awesome. We have basically got everything. We just need to write it up. We see that sine theta over theta is bounded between those two functions. Cosine of theta is less than or equal to sine theta over theta, which is less than or equal to 1 over cosine of theta. And this is for all theta not equal to 0. And we also know that the limit as theta goes to 0 of cosine theta is equal to 1, which is also equal to the limit as theta goes to 0 of 1 over cosine of theta. And so by the squeeze theorem, we now know that the limit as theta goes to 0 of sine theta over theta is equal to 1. So we have proven that using the squeeze theorem, and again, that'll be really useful to us later when we're finding derivatives for trig functions.